Some definition of Weber's fraction from the sense of hearing. The ratio of the smallest detectable change in the magnitude of a quantity to the baseline magnitude of that quantity. The magnitude of the quantity before the change was applied. In Weber's law, a general rule of perception stating that the smallest detectable change in a quantity is proportional to the magnitude of that quantity. In other words, Weber's law states that the Weber fraction is constant as a function of magnitude. Again, some definition from the sense of hearing. The Weber fraction is delta I divided by I, where I is the baseline of pedestal sound intensity, and delta I is the smallest detectable change in that intensity. The difference between the intensity of the higher level sound and the intensity of the lower sound level sound or pedestal, when the listener can just detect a difference between them. And expressed in decibels, the equation comes Weber fraction in decibel is 10 times log 10 of delta I divided by I. We continue. Results from a similar study on frequency JND. More, the red ones, data from shower, the green ones, and the average from the class. The Weber ratio dF divided by F in frequencies is almost constant for frequencies below 4 kHz. Other studies show that the ratio increases after 2 kHz. Okay, after 2 kHz. All the measures are below a semitone. Okay, small semitone change is about 5%, a little bit more. As you see here, the 12th root of 2 is about 1.959. So it's the JND for semitone is the semitone is similar to almost 6% change in frequency. The pitch of a complex sound. Two pure tones, P at T, the pressure of T. Pressure of at time T is sinus to 2 pi F1 times T plus sinus to 2 pi F2 times T. It's Act 2. Pitch of an equally loud two-tone sound. Yeah, if you make some simple paraphrasing in mathematics, sinus to 2 pi F1 times T plus sinus to 2 pi F2 times T is the same as 2 times sinus to the half. If you put those together, yes, arguments together and divide by 2, you get this sinus, and then the same times cosinus to the difference between those two half. Yeah, you can. And this sinus is a carrier frequency, and the other one is the modulation frequency, the other term. In the sense of hearing, it's written like this: xt is a times this parenthesis is a times sinus. The last term here is a carrier. Is a carrier of the pure tone, and the first one is a modulation. Yes, carrier frequency and modulation frequency. Yes. Pitch of are equally loud two two-tone sound. Pitch of an equally loud two-tone sound. We have this equation as before. If the absolute value of f1 minus f2 is less than 20, means same pitch as a tone at frequency f plus f2 half with an AM at f minus 2 half. So pure tone, I can listen to it now. I can't record it. Yeah, and the other one is 500 hertz pure tone, and if the half of f is 10 times difference. The complex tone is 500 and 510. It sounds a little bit different. Is AM stands for amplitude modulation. So the complex tone at for 500 and 510 hertz, those two frequencies, and the pure tone is the red one with 10 hertz. This is a pure tone. It's a pure tune with 10 hertz. Okay, we have case 1 with the absolute difference between f1 and f2 less than 20 hertz. This means same pitch as a pure tone at frequency f1 plus f2 half with an amplitude modulation of f1 minus f2 half. So a pure tone with 500 Hz and 510 Hz gives a complex tone of 500 and 510 Hz and an amplitude modulation of 10 Hz. Yes, the red one, pure tone, and the complex tone is a blue one. Now we see more clearly that the frequency is about 10. So there's 0.1 duration, what's called the T. One period is 0.1 second. Yeah. We need a little bit more understanding. A modulated waveform is from sense of hearing. Amplitude modulation. Imagine that you are playing a pure tone over your stereo and you vary the volume control on your amplifier up and down so that the overall level of the tone fluctuates. That the sound you would create is in this circumstance would be amplitude modulated. The original tone is called the carrier, and the slow up and down fluctuations are called the modulator. It's convenient to distinguish the rapid pressure variations of the carrier from the slower changes in the peak amplitudes of these fluctuations caused by the modulator. These two aspects of a signal are sometimes referred to as temporal fine structure and envelope. Figure 2.17. Amplitude modulation refers to variations in the envelope of a sound. Amplitude modulation can be produced by multiplying the carrier waveform with the modulator waveform. If the carrier is a pure tone and the modulator is a pure tone, the equation for the modulated waveform is that, see here, 2.5. And we have here XT is the pressure variation and A is the peak amplitude or pressure of the carrier. M is the modulation depth and FM is the modulation. We have an envelope here and a fine structure here. As figure 2.17, a segment of a sound waveform illustrating the temporal fine structure, thin line, and the envelope. There is also something called frequency modulation, whereas amplitude modulation refers to variations in the amplitude of a sound. Frequency modulation refers to variations in the frequency of a sound. So we have to be careful about those concepts. In music, rapid variations in frequency are known as vibrato. The silence used by police cars and ambulances are good examples of frequency modulation. Frequency modulation is also found in speech. Speech contains variation in fundamental frequency over time and in the frequencies of spectral features over time. Just as in the amplitude modulation, in frequency modulation we can distinguish the carrier, which is the original waveform, from a modulator, which is the waveform that describes the variation in frequency over time. So it's what we are about here. For instance, if the carrier is sinusoidally frequencies modulated, the frequency of the carrier will vary up and down in the pattern of a sine wave or pure tone. Yes, so we go back to this. This is a tone sound. Again, to be careful, we have the time here and the x-axis and the first axis and pressure of the second axis. The complex tone has a pressure of 2, maximum amplitude, and the pure tone has a amplitude of 1. So the blue one is a complex tone and the red one is a pure tone. Yes. Yips. So complex tones are mixed by 500 and 520 Hertz. It should give 500 to 510 Hertz. And the pure tone is 10 Hertz. Yeah, but I'm not quite convinced. Pitch of an equally two-tone sound. So again, if the absolute frequency difference is large, the two tones are perceived individually. They do not fuse. They can also be perceived as inharmonic. So pure tone, we can record it, 310 Hertz, 310 Hertz, and then a pure tone of 2500 Hertz, much more frequent, pitch is very different. The complex tone from 300 to 510 Hertz sounds less, yeah, a little bit inharmonic, yeah. And then the other one is more harmonic, where the difference between the frequencies are less than 20. Okay, so we have a complex tone here, 310 and 500, 2500, 310 and 2500 Hertz. It looks like this, yeah. And time, we have time here and pressure here. Here, 8 times 310 is almost 2500. 1 peak, 2, 3, 4, 5, 6, 7, 8. And again 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 small peaks that gives the big one. The small peaks, the frequency is about 2500 Hertz, and for the big one, from here to here, it's about 310 Hertz. It's a way to understand it. Same here with the other one, 500 and 510 Hertz. From here to here, from this top peak to this peak is about 0.1 second is 10 Hertz. Thank you.